Welcome to the 6th module of the E-content of the E-Pathashala series, lecture series in computer science. This module we are going to talk about the lexical phase still, where we are going to try converting the regular expression to a deterministic finite automata. In the previous sessions we have basically looked upon the phases of the compiler and focused more on the lexical phase, where we have to specify the patterns for the lexical phase. In that we looked at specifying patterns using the regular expression or the non-deterministic finite automata or the deterministic finite automata. So, the objective of this particular module is to construct an optimized or a minimized DFA. So, we already know that deterministic finite automata is going to be making string matching faster, because for every state on every input symbol there is exactly one transition. On the other hand, constructing a DFA is not easier, therefore, we resorted to constructing an NFA, which is a non-deterministic finite automata. Constructing that is easier. So, therefore, what are we going to do here is we are trying to use the best of both worlds, where we will be trying to construct first a non-deterministic finite automata, and then we convert that to a deterministic finite automata and make string matching faster. So, we have already done one part of it where we have already converted the epsilon NFA, ENFA. From that we have converted regular expression to an epsilon NFA, and now we are going to convert an epsilon NFA to DFA basically. But what is the drawback of this approach is this results in an increased number of states in the DFA. So, therefore, the number of states of the DFA need to be minimized. So, this minimization basically can happen in two ways. One is you can directly construct the DFA from the regular expression by using a new methodology. So, we have already looked upon constructing it to ENFA and then ENFA back to DFA, that is what we have done last class in the previous modules. On the other hand, you can have a direct construction algorithm which is going to construct the automata, deterministic finite automata, which is a minimized one, directly from the regular expression itself. Or we can go in for a table filling minimization algorithm, where you would construct a DFA using the regular expression to ENFA and then to DFA procedure, and then have an approach to use this constructed DFA and then try to minimize this by eliminating redundant states. So, in this module we are going to talk about the first approach, where we are going to construct the DFA from the regular expression. The first step in this is going to be augmenting the regular expression with a hash symbol. So, this will tell you the end marker basically. So, this indicates that the regular expression is basically over, and then after that we have to construct a syntax tree for the regular expression followed by the hash string. So, you have the regular expression and you have augmented that with a hash string. So, for this modified regular expression you will basically construct a syntax tree, and then you have to traverse the tree to construct the following functions. The first function is called as nullable, the second one is called as first position, third one is last position, and then following that you have the follow position. So, this is how it is going to look like. Let us take the same example which we used in the previous modules, where we have the expression as a or b the whole star followed by ABB. So, what we have here is a or b the whole star, therefore, it is either a or b. This is the OR node basically. So, this is going to be the OR node, okay, and then whole star of that. So, I have it here, and then followed by there is a implicit concatenation operator dot here, and there is going to be a hash which is terminated after this, okay. This is your R followed by hash. So, this is your a or b the whole star followed by a followed by b followed by b and then followed by hash. So, as you could look at, the interior nodes are basically the operators, and the leaf nodes typically are going to be your terminals, okay. So, supposing if I have an expression something like a or b star, okay. So, how does this going to be? I am going to have a hash after this. So, where I will have the node as a here, and then it is going to be a or b star, okay. So, I have to first do a b star because star has a higher priority compared to the OR operator. So, I will do a B star. So, B is my leaf node and its parent is going to be a star node, and I have a OR operator for this expression, and followed by that I have a hash. So, it is going to be dot followed by hash. This is how the tree is going to look like if it is going to be of this particular expression A or B star. Okay. So, after doing this, that is your first procedure. After constructing the syntax tree, now we have to find out the functions nullable, first position, last position and follow position. The first thing is to find out the nullable nodes. Now, for every node we have to compute all these functions: nullable, first position and follow position, and of course last position. After that, we label this tree still further with all these function values, and then we are going to use that for determining your DFA. Now, we just number the leaf nodes in an arbitrary manner. You can just use any methodology. This is from the textbook Ahoseti-Ullman. So, where I have numbered it as 1, 2, 3, 4, 5, 6. So, the leaf nodes are basically numbered. Now, after that we are going to construct these functions. Now, we call a node as nullable. The subtree at node n generates languages including the empty string. If it could generate empty string, then I will call the interior node as nullable node. And the first position is defined as set of positions that can match the first symbol of a string generated by the subtree at node n. So, for example, if you look at the previous tree, what is going to be your first string? The first string is basically ABB. Then I can have a prefix with A or a prefix with B. So, the first position of this particular regular expression is going to be definitely A. Okay, so this will basically be the first position. So, what is the string that could occur as the first character? That is what we call it as a first position. And follow position basically means what will follow a particular symbol, a particular character. And similarly, the last position of a node n is set of positions that can match the last symbol of a string generated by the subtree at node n. So, first position and the opposite is going to be last position. What could be the last character basically? And follow position of I is a set of positions that can follow position I in the tree. So, what symbol we can follow? Basically a previous symbol. That is what we are talking about as follow position. So, first position is which character could occur first, last position is which one could be the last possible string, and follow position is after a particular character what can basically follow. So, this is what we talk about as three functions. And nullable is, we will call a node as nullable because it can generate the prefix as going to be an epsilon string. Okay. So, with that in mind, we are going to define rules for doing this. Now, supposing a leaf is labeled with an epsilon value, then nullable of that particular node is going to be true. Okay. And the first position of that node is null and the last position of that node is also going to be null. So, this is how the definition of epsilon basically holds for. Supposing you have a node n and if that is going to be a leaf node, okay, and then the nullable of that particular node is going to be true, okay, and then the first position of that node n is going to be null and the last position is going to be also null. Supposing if the leaf is labeled with any other character I, okay, call it as any other character I, call it as A, B or whatever it is, any input symbol A or B, then I will basically say the nullable of that particular node is false. Okay, this is obvious. Supposing a particular node has got epsilon as its value, then from that node whose where that is going to be a subroot or subtree, from that particular thing I can generate an epsilon string, that is a possibility. Whereas supposing if I have got a node labeled with I, which is a non-epsilon value, I cannot get an empty string. So, therefore, it is going to be a nullable of that particular node is false. And first position is I, last position is also I. Now, after that, this is for the leaf node. Now, we look at the interior node. Now, I have a OR operator node here. I have rules for the dot operator and the star operator also. So, for the OR operator, it will have two children maximum, okay, C1 and C2. definitely as OR operator will have 2 children, a dot operator will also have 2 children, whereas a star operator will have only 1 child. So, the nullability of this particular node, that is the nullability of your OR operator node depends upon the nullability of its children. Okay. If for example, C1 is nullable or C2 is nullable, any one of them is nullable, then I would call this as nullable. Now, this is again obvious because when we say OR operator, what do you mean by A or B? It means that either string A or string B. What is the definition of nullable? We said a node is said to be nullable if it could generate an empty string. Okay. Similar, therefore, if C1 is nullable, when will C1 become nullable? According to the 2 base rules. One is the leaf is going to be labeled with an epsilon value. So, if this is going to be epsilon, then I would call this node as nullable, because this node is capable of generating an empty string using the left subtree which is rooted at C1. Or on the other hand, if C2 is epsilon, then I can say that this interior node has a capability of generating empty string using the subtree rooted at C2. So, nullable is defined of the OR node supposing if C1 is nullable or if C2 is nullable, I would call the interior node also as nullable. And first position of this node is defined as first position of C1 union first position of C2. Similarly, last position is defined as last position of C1 union last position of C2. This is a very simple case. Okay. Which means that either I could start with the character belonging to C1 or I could start with the character belonging to C2. Similarly, for last position. Okay. And for this for the interior node, which is labeled with the dot operator. For the dot operator, it depends upon nullable of C1 and nullable of C2, which means that C1 should be nullable, and if C2 is nullable, then this is capable of generating a empty string. Now, supposing if C1 alone is nullable, supposing say I have an epsilon here in place of C1. Okay. I have an epsilon here in place of C1 and I have a character A here in place of C2. Now, what is the string corresponding here? I have epsilon A, it is no longer an empty string. Okay. So, therefore, only if both are epsilon, this interior node will be epsilon, which is nullable, else it is not going to be nullable. On the other hand, for first position, if C1 is nullable, then first position of C1 union first position of C2, else it is the first position of C1 alone. That is, if C1 is nullable, then this node's first position is nothing but union of these 2 first positions, else it is just this first position of C1 alone. Similarly, with last position, I will look at nullable of C2. If C2 is nullable, then last position of this interior node is the last position of the union of these 2 nodes, else it is last position of C2 alone. Okay. And similarly, with this condition, a star node, if C1 is nullable, then this star node is going to be, again, star node is always nullable. Okay. So, it does not depend upon C1 or C2, but it is always nullable. Why? Because star means 0 or more combinations. 0 or more combinations means it is going to generate an empty string definitely, A or B the whole star. What does it mean? It simply means that 0 or more combinations of A or B. What is the first string there? The first string is obviously epsilon, A star. The first string is obviously going to be epsilon. So, definitely this for the star node, which is the clean closure operator node, nullable is always true. And first position will be first position of C1, last position will be last position of C1. So, with these basic rules, we will try to construct and annotate the already constructed syntax tree. So, we have got the syntax tree here. Okay. For this particular tree, let us try to construct the nullable first position and last position values. So, okay, let us just take the leaf nodes. This is already labeled. Let us just take the leaf nodes first, A, B, and hash. So, we are going to number it with the number which we have assigned to the nodes 1, 2, 3, 4, 5, 6. Why do we number it as? This is going to be corresponding to your state number of your automata, of your DFA, which is going to construct it later. Okay, so just for that particular purpose we have numbered it, and we are going to use it for all our scenarios. Now we already say A. Okay, so supposing for a leaf node, if it is non-epsilon, then first position is itself, last position is itself, and these are not nullable nodes. Okay, so first position is 1 and 1, last position, this is according to the second rule. Okay, leaf of I, if it is going to be any other leaf node, nullable is false, and first position is I and last position is also going to be I. So with that in mind, this has got first position as 1, this is your the one on the left is first position, the one on the right is going to be last position. We have still not calculated follow position. Okay, so first position is 1, follow position is 1, sorry, last position is 1. Similarly here first and last positions are 2 and 2, first and last position are 3 and 3, last position are 4 and 4, 5 and 5 and 6 and 6. So this is over. Now we have to look at the first position of the interior nodes. Now the interior node with, I have all operators possible here. For the OR operator it is very simple, if you remember that. It is simply first position of C1 union first position of C2 and last position of C1 union last position of C2. So here only one node is there. So it's this node's first position is 1, 2, this node's last position is 1, 2. So that is the end of this particular node. So for the leaf node it is just the same number itself. If it is non-epsilon, I do not have an epsilon here. If it is an interior node with an OR operator, then the first position will be union of the first position of its children, and again last position will be the union of the last position of its children. Now let us just traverse the tree. I have a star node. Okay. For the star node, again first and last position are very simple because it is just the child's first and last position. So for this particular node, okay, first position is again 1, 2, which is from the child, and last position is also 1, 2 from the child. Now only for the concatenation node we need to check whether the left child is nullable or the right child is nullable. We already know that none of the right children are nullable, A, B, B hash, none of them are nullable. Only that I have this node being nullable, okay, because we already know a star node is nullable by default. Okay, a star node is definitely nullable. So for the interior node, okay, it is nullable of C1 and nullable of C2. Okay, so both the children should be nullable for the parent to be nullable. So here only one is nullable, this is definitely not nullable, therefore none of the interior nodes are nullable except the star node. I think I get this point very clearly here. Only the star node is nullable, there is no epsilon symbol, and therefore for the interior node here with the dot operator, okay, this node, this is C1, this is C2. Okay, this is C1 and C2, and for this node this is nullable by default because a star node is always nullable, and this node is not nullable. So therefore this node is not nullable because it is nullable of C1 and nullable of C2. So this node is not nullable. Since this node is not nullable, none of the interior nodes are going to be nullable. Okay. So therefore we need not worry about nullability. Only for computing this node we should look at nullable of C1 or nullable of C2. Okay. So let us look at that rule. If C1 is nullable, then it is first position of C1 union first position of C2. So this is nullable. So first position of this one will be union of the first position of its children. So 1, 2 is the first position here. Here it is 3. So the first position of this particular node is 1, 2, 3. What about last position? If C2 is nullable, then it is union, else it is last position of C2 alone. So here this is not nullable, therefore last position of this node is only 3. Okay. So here for this interior node, left child is nullable, right child is not nullable. So C1 is nullable. Since C1 is nullable, first position will be the union of the first positions of this and this, which is 1, 2, 3, and last position is simply the last position of C2. Now for this interior node, C1 is not nullable. Okay. So if C1 is not nullable, if C1 is nullable, it is union of the two. If C1 is not nullable, then it is simply first position of C1 alone. So I have here for this node first position of C1, which is 1, 2, 3, and similarly here last position of this node will be last position of C2, which is only 4. Okay. So for this node and correspondingly for this node and for this node, the last position and first position will be correspondingly from C1 and C2. So this node's first position will be from this node, this node's last position will be from this node, this node's first position will be from this node and last position will be from this node. Similarly for this node, first position is from its left child, last position is from its right child. That is what it basically says here. If it is not nullable, then the first position of the node is the left child's first position and the last position will be the last position of C2. This is again obvious, it is a concatenation operator, C1 followed by C2. So first position will be what is done by the left child and last position will be what is done by C2. So this is how you compute. Then after computing these, we have to compute the follow position. So follow position is basically done for all the nodes, all the leaf nodes 1, 2, 3, 4, 5, 6 by following this procedure. For each node n in the tree, if n is a cat node is concatenation node with left child C1 and right child C2. Okay. Then for each I in last position of C1, do follow position of I will be follow position of I union first position of C2. If n is a star node, then for each I in last position of n, follow position of I is equal to follow position of I union first position of n. So I have to look at these two nodes. I have to look at the cat node and the star node, that is the concatenation node and the star node for performing the operation of for computing follow position of I. Now what is I? I is going to be from the list available in last position of C1, where what is C1? C1 is the left child of the concatenation node. Okay. So let us look at this. Let us take a concatenation node here, which is this node. Okay. So this is a concatenation node, and concatenation node, what should I look for? For each I in last position of C1. Okay. So for this is a concatenation node, its left child is this one, right child is this one. So this is the left child. So left child's last position is 1, 2. Okay. So I have to look at the follow position of 1 and follow position of 2 is what I am trying to compute now. Okay. So this is my cat node, this is my left child, this is my right child. Left child is C1, right child is C2. My algorithm should look at the every element in the last position of C1. Okay. For each I in last position of C1, do follow position of I is equal to follow position of I union first position of C2. Okay. So what does it mean? For I have to look at the nodes 1, 2. So follow position of this will be follow position of 1, okay, follow position of 1 union first position of C2. Now what is C2's first position here? 3. So definitely in 1, 2 I will get 3. In 1, 2 I will basically get 3. So we are looking at follow position. So look at this interior node. This interior node will basically have a dot 1, 2, 3 as the first and last position. Its children has got 1, 2 and 3 as the first position, and last position will be 1, 2 and 3 here. So look at this, it says follow position of I. Okay. Follow position of I. What is I actually? I is available in last position of C1. So C1 has got 1, 2. Okay. So sorry, 1, 2 here, last position. So last follow position of 1 and follow position of 2 will definitely have first position of C2, which will definitely have 3. Okay. So that is what I have got here, will definitely have 3. Okay. And what about the other two? If you look at the star node, if n is a star node, for each I in last position of n, do follow position of I is equal to follow position of I union first position of n. First position of n is your star node basically. So, for each I in last position of n. So, this is my star node. For each I in last position of n, that is one for 1 comma 2, you will say follow position of I union first position of n. Okay. Follow position of I, which is 1 comma 2 union first position of n, which is first position of n is 1 comma 2. So, 1 comma 2 will be included in the follow position of 1 and 2 respectively according to this logic. So, this is my star node, this is n. So, this will basically have, for the follow positions of 1 comma 2, I need to include the first position of n. First position of n is going to be 1 comma 2. So, I will include 1 comma 2 there. So, based upon that logic, I have got 1 comma 2 comma 3 here. Okay. And then if you remember that for the remaining logic, if it is a cat node, so I will go to the next node here. We have done with reference to this. For this 1 comma 2 comma 3 and a 4 I have here. Okay. So, for each I in last position of C1. So, this is my last position of C1, which is 3. Okay. So, 3 will basically have first position of B, which is 4. So, that is how I have 3 will have 4, 4 will have 5, 5 will have 6 and 6 does not have anything. So, this is according to the first rule, which is nothing but this rule for each I in last position of C1. So, last position of C1, if you remember, it has got 3 here, 4 here, 5 here. Okay. So, for and 6 here of course. Okay. So, this is your n, this is C1, this is C1, this is C1. So, this C1's last position will basically contain the first position of C2. So, which is nothing but 4. That is how the algorithm basically look at. Okay. So, why do I say here follow position of I? You have to keep on accumulating. To start with, follow position of I will have null. Okay. You have to add upon it. You should not replace it. You have to basically add upon it. So, after computing that, we will basically use this algorithm to compute your automata. So, let us look at S0, which is the first position of the root, and where root is the root of the syntax tree, and D state, the states are going to be S0 and is basically unmarked. So, what do we do here? Look at the root. The root has the first position as 1 comma 2 comma 3. So, that will correspond to your start state. Okay. So, that corresponds to your start state, and then you have to look at 1 comma 2 comma 3 on A. Okay. So, what do we do here? Well, there is an unmarked state T in D states, mark T, and for each input symbol A belonging to sigma, do let U be the set of positions that are in follow position of P for some position P in T, such that the symbol at position P is A. If U is not empty and not in D states, then add U as an unmarked state to D states. Now, this is actually the algorithm which is given in the book. Let us just look at it very simply in a simplified fashion. I have 1 comma 2 comma 3. Now, look at the tree, the syntax tree. The syntax tree has got 1, 2 and 3. Now, out of these 3 nodes, 1 and 3 belongs to A. Okay. So, you should look at transition on 1 on A and transition from 3 on A. So, 1 comma 3's follow position on A, where does it take you to? Okay. 1 comma 3 follow position takes you to 1's follow position is 1 comma 2 comma 3 and 3's follow position is 4. Okay. Nodes 1 and 3 corresponds to the symbol A. So, nodes 1 and 3's follow positions are 1 comma 2 comma 3 and 4 respectively. Therefore, you will basically have to go to 1, 2, 3, 4 on A from 1, 2, 3. Remember that only 2 contributes to B, 1, 3 contributes to A. 1's follow position is 1, 2, 3, 3's follow position is 4. So, this on A goes to 1, 2, 3, 4 and 2 contributes to B. So, 2's follow position is the same 1, 2, 3, because if you remember the table here, follow position of 2 is 1, 2, 3. Okay, so 2 on B is 1, 2, 3. Now similarly here for the next state 1, 2, 3, 4, again if you remember 1, 3, this will contribute to A, 2 and 4 will contribute to B. So again 1, 3's follow position will be 1, 2, 3, 4. Okay, we will probably take a break here, we will resume in the next session. The same example, we will continue with that. As of now, we have basically done the automatas, the algorithm to construct the regular expression from the DFA, the DFA from regular expression directly. Yeah, so we are in the middle of converting the regular expression to DFA directly, which is going to be a minimized one. We will resume this in the next module. The same example we will continue with that, and then try the other methodology to construct a minimized DFA from a given DFA. Thank you.